Welcome everybody to another seminar with the Virtual Time Series seminar. It's my pleasure to introduce Zhentao Shi, and he's joined by Andrii Babii, and the topic is econometric inference for high-dimensional predictive regressions. So, Zhentao, the stage is all yours.
Yeah, thank you for having me. It's my honor to present in this virtual time series seminar. So this is a direction of research, and I've had 3 papers along this topic. So let me quickly introduce the first 2, and then I'll go into detail in the current paper that I'm gonna present today. So the first paper was published in 2022. This is a collaboration work with Jihong Li from UIUC, and Zhang was a master student of mine in CUHK, and now he's an assistant professor at Southern Methodist University. In this paper, we talk about the behavior of adaptive lasso in predictive regressions, and the focus was on the variable selection. And this paper is about low-dimensional regression, that is, the number of regressors is fixed. Then, of course, we know when we use lasso, our purpose is to handle high dimensionality. In the second paper that I worked out with my PhD student Ziwei Mei, who is now in University of Macau, we worked on lasso with high-dimensional predictive regression, meaning that the number of regressors can be larger than the sample size. And the main technical challenge there is to handle the restricted eigenvalue condition when a lot of regressors are non-stationary. So today's paper is gonna go one step further and look at the inference problem. Since the second paper was only about consistency, about the rate of convergence, but we're gonna work out the asymptotic distribution when we are interested in some particular parameter. These 3 papers want to provide a theoretical foundation for the machine learning methods. And lasso, of course, is the off-the-shelf machine learning methods. If we don't understand the property of lasso, then it would be very difficult for us to understand more sophisticated machine learning methods. And unlike the statisticians who mostly work with IID data, we work with time series context, in particular non-stationary time series, and when needed, we are gonna recast the machine learning methods to tailor it and make it for our economic purpose. So we will see that in this paper, indeed, we need to modify the existing procedure in order to get what we want in non-stationary time series. In case some audience is not very familiar with predictive regression, then let me just briefly introduce the predictive regression in the classical context. We want to predict a yt with some xt minus 1. For example, the most well-known example is to predict stock return. In this case, the yt is an SP500 excess return, and xt are some other regressors. For example, in this very famous paper by Welch and Gallia in 2008, we used the data from 1945, and the dependent variable y is S&P 500 excess return, and these are the 12 potential predictors that displayed in this paper. And there are many ways to do prediction. Say you can try to put these regresses one by one, or we can try to put all these regresses together in a so-called kitchen sink approach. One defining feature of the predictive regression is that oftentimes these regresses can be persistent. We will show in the next two slides that we will see the graphs of this time series. Some time series can be quite persistent, and in this talk, I will just use a exact unit root process to represent a persistent regressor. If the regressor is persistent, then if we run an OLS regression in this main equation, the OLS estimator beta 2 hat will follow a unconventional asymptotic distribution. Therefore, the statistic inference is gonna be unconventional too. So it will be a non-standard asymptotic distribution. So we will have a unconventional statistic inference. That's the main challenge in the existing literature that mostly work with low-dimensional regressions. So this is a graph of the dependent variable. If it's a monthly return, then it's very much look like a white noise. If we aggregate over a longer predictive horizon, then the y variable can be more. We have seen stronger time dependence, and there's more hope to achieve prediction. And then these 12 small plots are exactly the 12 regressors that are included in Welch and Gallier's original paper. You can see they have very different patterns. For example, this BM time series looks very much like a unit root process. It's very persistent. This LTR time series is mostly fluctuating around the mean and with different volatility, but it's like a stationary with a stable mean. And more interestingly, there are some time series very much look like co-integrated time series, right? For example, this DP time series and DY time series, the plot are very closely resembling each other. Or we also see this TMS and the DFR time series. They are also very similar, right? So in this zoo of potential regressors, there are all kinds of time series of different patterns. So with the spirit of machine learning, we would like to keep an agnostic attitude. That is, we don't want to do pre-testing to distinguish which time series is I1, which time series is I0. Instead, we would like to provide a unified procedure that can handle all sorts of regressors in a simple procedure. So here, this is the setting of the paper. We consider a multiple regression. The time series has sample size t in the sample size n indexed by t, and this is a multiple regression with p regressors. And we all know that if there are a lot of regressors, we need to do some regularization. And one of the off-the-shelf method with variable selection effect is lasso. Lasso is to append a L1 penalty to the standard OLS criteria function so that it will have the effect to shrink some coefficient to exactly 0. The original paper by Tibshirani in 1996, he use so here this tau j hat is a weight in front of each beta j, and this lambda is the tuning parameter, right? So the original paper by Tibrani uses a uniform level of penalty, that is, all these weight are set as 1. But this we call it the plain lasso or abbreviate as P lasso. But P lasso has the problem that if you change the unit of xj, then the beta is not gonna change proportionally so that it will affect the in-sample fitting. Therefore, in computer software, for example, if we look at the default option in R or in Python, the implementation is actually the standardized lasso, which I abbreviate it as S lasso. S lasso is just to use this tau j as the sample standard deviation of the j's time series. With this scale standardization, when we change the unit of the j's regressor, then the coefficient will change proportionally so that it will make sure that the in-sample fitting is going to be invariant. So this is the standard implementation in software. In the statistics literature, people do not pay much attention to the difference of P lasso and S lasso. That is because with RID or weekly stationary time series, then the sample standard deviation will converge in probability to a constant. Therefore, the choice of tau equal to 1 or tau equal to sample standard deviation, they only differ with a constant, right? It does not change the convergence rate at all. But if we have a time series of very different patterns, then the picture is completely different. That is because, suppose, for simplicity, let's think about some x are exactly I1, then the unit root process will have the standard deviation of a big OP square root to n order. More precisely, if we standardize it by square root n, then this object, this sample standard deviation, will converge to the square of a Brownian motion, the integral of square of Brownian motion. Therefore, even if we standardize it by square root n, this sample standard deviation will not converge to a constant. And this dramatic scale will substantially affect the penalty level associated with these coefficients, right? So no one has investigated this problem before with different scales of the standardization, the penalty in standardization. So this is the main topic in the second paper by my student Ziwei Mei. So in this paper, we look at high-dimensional regression, and we want to find consistency. What method can give us consistency with a high-dimensional regressor when P can be greater than N, and asymptotically P can be much larger than N? So we started with a unit root regressor. So because I want to introduce this paper because our asymptotic inference is gonna build on the consistency result, right? So consistency is the prerequisite. So I'm gonna use 3 slides to introduce the result of this paper, and then we go to the current paper about asymptotic inference. So we start with the simple model when all regressors are independent unit root processes. And we know with lasso, we need a sparsity assumption, right? Although we have a very large number of regressors, but those regressors with non-zero coefficient, it must be much smaller than the sample size. Otherwise, there's no way to use lasso to do a reasonable good estimation. One of the key conditions for lasso to work is this restricted eigenvalue condition laid out in this famous paper by Bickel, Ritov, and Sibakov. So here, the central piece is the Gram matrix. It's the sample covariance matrix sigma hat equal to x prime x divided by n. When p is greater than n, then this sample covariance matrix must be rank degenerate. Therefore, the minimum eigenvalue must be 0. And with the sparsity assumption, this paper puts the restricted eigenvalue, meaning that the vector, when we evaluate the eigenvalue, is going to be considered in this restricted set. The restricted set is to say, here, this M is the index set whose cardinality is smaller than S. S is the sparse index. And the restricted set consider all these vectors whose most of the mass if measured by the L1 norm is concentrated in a small subset. And then the mass in the rest of the the rest of the coordinates is measured by the L1 norm, and this should be so it should be smaller or equal to a constant than the L1 norm in the small set. This particular constant 3 doesn't matter as long as it's greater than 1. So, sorry, what? I think whenever I click it, move to the next. This may be because of it is in the shared mode, which is not what when I do rehearsal, it was not the case. So yeah, excuse me for the for the click. So the restricted eigenvalue is gonna be bounded away from 0 when the underlying regressors are either RD or weakly stationary. So this is one of the key components to show the consistency of lasso. But imagine in the extreme case when all these regressors are independent unit roots, then the result is completely different. We find that the RE, the restricted eigenvalue defined this way, actually, surprisingly, it goes to 0. But the good news is that it goes to 0 at a quite slow speed. Therefore, with this slowly going to 0 restricted eigenvalue, it is still possible to show the consistency of lasso, even though we are faced with a high dimensional of unit root processes. The convergence rate of lasso will pay a price of log p, but this log p can be accommodated because we have unit root regressors and they actually have a strong signal. So we will have almost like a super consistency rate of convergence multiplied with some log p price. So that is tolerable. Now, in reality, we have different types of regressors. So consider the simple case when there are two categories. One is L1 regressors. The other is L0 regressors. And in reality, we have them mixed together. We don't distinguish which is which. We argue that in this case of mixed type of regressors, we should not use the P lasso. That is the original proposal by Tibshani. That is because the P lasso set all these weights to the coefficient equal to 1. But the mixed regressor case, the highly persistent regressors and these stationary regressors, they have very different behavior. There is no way to use a uniform level of penalty to handle these two types of regressors. It will be inconsistent. So the P-lasso is going to be inconsistent when we have a mixture of I1, I0 regressors. But the good news is S-lasso still works because S-lasso has a self-normalization effect. The heavier penalty coming from the standard deviation of the I1 regressors provide a stronger level of penalization to those associated regressors, and this is exactly what we want. So we can indeed show the consistency of S-lasso with a mixture of regressors. So these are the results of the previous paper when we established consistency. Now let's move on to the current paper when we work with statistical inference. This paper is a tribute to Irving Fisher, who is a pioneer to provide statistical inference to check economic relationship. Fisher proposed a lot of very famous theories in microeconomics, including the monetary quantity theory, inflation-deflation theory, and index theory. In Fisher's time, he used a very simple model because he has limited data. Now we have abundance of big data, and we want to provide a perspective with more capable model that motivates us to use high-dimensional regressions. On the other hand, economists care about statistic uncertainty. Therefore, we are interested in statistic inference. Today's economists love stars, right? The stars can help us to provide a better interpretation and understanding of the economic relationship. Therefore, we want to look at the important problem of statistic inference. When we look at the literature of statistic inference after lasso estimation, there are mainly two approaches. One is under the umbrella of the biased lasso, represented by this Zhang and Zhang paper in JRSSB, and also those papers published in the same year. These papers have different idea, but the underlying principle is the same. It's to, after you estimate with lasso, you try to figure out what is the bias, and then you compensate the bias so that you have a de-biased estimator. These three papers study the procedure that is valid under RID and stationary regressors, but they cannot be immediately carried over into non-stationary time series. Another approach which has been very successful in econometrics is the double machine learning approach. Double machine learning approach is particularly tailored for RID data because it requires sample splitting or cross-fitting. But when we think about non-stationary time series, if we cut to the first half of the data and the second half of the data along the time dimension, then they will have different initial values. Therefore, the theory is not going to work with non-stationary time series. So this paper, our approach is inspired but tailored with this de-bias lasso approach by Zhang and Zhang. This, to the best of our knowledge, this is the first inferential procedure that is valid for high-dimensional unit root regression with unit root. And we're gonna, again, just follow the setting of the previous paper. We will work with a mixture of I1 and I0 regressors. Our procedure will work no matter the key variable of interest is associated with I1 or I0 regressors. So here, this is the object of interest. Our goal is to conduct inference with a low-dimensional coefficient. To make it simple, in our current version, we will allow joint test, but for this talk, we just keep it as the previous version. We deal with a single coefficient. Without loss of generality, we call it theta 1 star. Usually, we are mostly interested when the null equal to 0. And on the right-hand side, we can have a mixture of I1 regressors, I0 regressors. We don't distinguish which is which. So put them together, we call the mixture of regressors W. Since we are particularly interested in the first regressor, so we highlighted the W1 associated with theta 1 star, and the rest of the regressors we denoted with W diamond. In Econometrics PhD 101, we all know that if we run ORS, the first coefficient of ORS can be estimated by 2 ways, by the Frisch-Wall and Lobwell theorem. The first approach is you just run an ORS with all the regressors and pick out the first coordinate, right? This is the most straightforward. Alternatively, we can regress the first regressor to the rest of the regressors with ORS, and we save the residual from this regression. Next, we use this formula. Basically, this is very much like a two-stage least square formula, but here the IV that we use is just like the residual from the first regression. This is not IV regression, but anyway, this is the FWL theorem. So by this approach, we can get exactly the OLS estimator for the first coefficient. Now, if we follow this idea, we can no longer use OLS regression, because think about when P is greater than N, then the first regression will produce exact ensemble fitting, perfect ensemble fitting, so the residual becomes 0, right? That would not work. So let's first think about somehow we replace the ORS residual by some score called RT. I will be specific how we constructed this RT. So let's say if we already have an RT, then the estimator of the theta 1 star follow the previous expression can be written as something like this. We just replace the R hat LS by this generic score RT. So we call this a linear estimator, which is linear in Y. Okay, now with simple linear algebra, we can decompose the first formula into 3 parts. The first part is the true regressor of interest. The second part is a bias object that is gonna move the center, and the third part is the score multiplied with the error term. So we will hope this term can follow a normal distribution. This term should be centered at 0, and we hope this term will follow a normal distribution. So I will use B to denote the red part, and use n for like normal to denote the blue part. And we will analyze these two terms one by one. All right. Because we are in the high-dimensional world, we cannot use ORS to do estimation. We're gonna use the S-lasso, as in the previous paper we have shown. It works well with a mixture of I1 and I0 regressors. So this will be our baseline regression. After we run this S-lasso, we will have the long vector S theta hat S. S is for standardized S-lasso regression for this S-lasso. And then if we have an RT, then we can estimate the bias term, the red bias term with this formula, right? We just replace this true value by the estimated value. And then we want to debias the linear estimator in the hope to get a good estimator that is centered at 0. So if we can estimate the standard error well, then we would like to construct a t-statistic. That is, the t-statistic will have two components. The first one is the blue one. Hopefully it is a normal distribution. And the second one is the bias, is an estimate of the bias. So we hope that the gap between these objects is going to be asymptotically negligible, so that our t-statistic should center around 0. Therefore, our goal for the construction of the score is the following. We want the first object to follow a normal distribution asymptotically, which requires that the RT-1 to be less persistent than local to unity, right? Because in case this is very persistent, like a unit root, then the whole object will converge to a non-standard distribution, then asymptotic normality would not work. Only when this is not that persistent, we can have asymptotic normality. So it gives a hint of the construction of this RT-1. It imposes some requirement. Secondly, for the bias term can be decomposed into two terms. The first term is an inner product of the score with the rest of the regressors, and the second is determined by the quality of the baseline estimator. So the baseline, we know that what's the convergence rate of the baseline estimator from the previous paper, but we need to make sure that the first term cannot be too big, right? So that it requires weak correlation between this score R and the rest of the regressors. So the key is how to construct a desirable RT that can satisfy the requirement in both the N term and the B term. So here is our construction. The inspiration comes from the paper by Magdalenos and Phillips, 2009. Their paper works in a low-dimensional regression context with persistent regressors. And the way that they recover asymptotic normality is to introduce the self-generated IV. Self-generated IV means it will be a two-stage least square regression, an IV regression, but the IV is not coming from outside the system. Instead, it is constructed by the X regressor itself. So how do we construct it? The construction is very simple. We just constructed this new IV called zeta t. It is constructed this way. We take the first difference of the persistent regressor So in our case, it does not have to be persistent. It can be I1, it can be I0. But in their paper, it was started with a persistent regressor. So we take the difference of persistent regressor and multiply it with the proper power of a rho z that is close to 0. So the rho z is something constructed by the user. The usual choice is something like this. The rho z is 1 plus cz divided by t to the power of tau. This cz is a negative constant, and this tau is a constant that is strictly between 0 and 1. So these are two hyperparameters. Usually, in this literature of IVX, the focus is on the choice of tau, and the literature suggests that we should choose a tau that is arbitrarily close to 1 to maintain the strength of the signal from non-stationarity. We will see our paper will provide a different recommendation. In this IVX paper, if we think about the W1 is a unit root, then with this construction, this zeta t, the newly constructed self-generated IV, will be mildly integrated. And with the functional central limit theorem in low dimension, we will see that this blue n object can indeed be asymptotic normal. But the problem is that in their context, their paper analyzed a simple regression. They only have one regressor. But in our paper, we have a large number of regressors. Some are I1, some are I0. And then this mildly integrated zeta t actually introduced one more type of persistent regressors that have different orders from the other persistent regressors. So how should we proceed? Our proposal is the following. This is the approach to construct the score. If the zeta 1 is I0, then if we just follow the IVX construction, the zeta t will behave similarly to the original time series. So we need to decorrelate between the zeta t and the I0 component in this rest of the regressors. Therefore, in order to deal with the scale problem, first we need to scale normalize the self-generated IVX. This is something that was never considered in the low-dimensional IVX literature because there was no need to do it. In our case, because we have mixture types of regressors of different scales, therefore this standardization step is necessary. The second step, we need to regress the newly constructed IV on the rest of the regressors W diamond. And because this is again a high-dimensional regression, we again use S-lasso to do this estimation. And this estimation is essential to decorrelate if this one is I0 and there are other I0s correlated with it. Therefore, this is our ultimate construction of the score RT hat. We have discussed that when the true regressor of interest is an I0, then this auxiliary regression is a must in order to decorrelation. If the true regressor is I1, then the auxiliary regression is actually unnecessary. We only need to do a scale standardization. The auxiliary regression is actually unnecessary. But again, because we keep an agnostic attitude. We don't want to distinguish at the first whether it's I1 or I0. Therefore, our design of the RT hat is to accommodate both cases of the different types of the regress of interest. So now I have described the algorithm, and now let's go to the assumptions, and we'll quickly go over the theoretical results. So we require the following assumptions. We need the shocks to the regressors to be stationary and ergodic. And these shocks are a linear transformation of some underlying epsilon j. This epsilon j should be independent over j, but they can be theory correlated. This phi big matrix should have all singular eigenvalues bounded away from above and below so that they are well behaved. For the marginal distribution of this epsilon and this ut, the ut is the error term to the main regression. That is the shock to the y. Say their marginal distribution should have a sub-exponential tail so that they are relatively of a thin tail in order for us to handle high dimensionality. And interdependence, say, should be exponentially decaying alpha mixing. And moreover, we assume an MDS error in the main regression's error term in order to avoid the complexity come from long-run variance. So these are the main assumptions about the underlying shocks. And next, we also need to impose restrictions on the dimensionality of the problem. Here, the number of regressors is P. It can be of a power order, polynomial order of n. Here, when this v is greater than 1, then we do allow the p can be much larger than the sample size n. So this is the genuine high-dimensional contest. We also need to impose restriction on the sparsity index, because if it's very dense, then lasso will not work very well. Here, we find that the maximum capacity to handle sparsity actually is related to the choice of the tau when we construct the self-generated IV. So here, if tau is very close to 0 or very close to 1, then we can only allow very sparse case. Therefore, but tau is selected by the researcher himself, right? Therefore, in order to accommodate a denser model, we recommend that we should use tau. We should set tau equal to a half so that we can at most allow the sparsity index to be n to the power of the eighth. So this is a key difference from the low-dimensional know-how of IVX, because in that literature with low dimension, they recommend we choose the tau as close as possible to 1. But in our case, in order to accommodate a lot of non-zero coefficients, we want this tau to be a half. So we would sacrifice a little bit rate of convergence to accommodate more models. All right. Our method is based on the consistency, so we will directly apply the results from the previous paper. This is a very ugly slide, but the main message is just to say that if we choose the tuning parameters in lasso at a proper order, then we can have consistency of the S-lasso estimator in the regression with proper rate of convergence. And the same is true, the same consistency is true in the auxiliary regression when we construct the score. And with the consistent estimator, now we can debias the estimator to construct the t-statistic. So this slide is the main result of the paper. It says that if we choose the tuning parameter in the main regression properly, the tuning parameter in the auxiliary regression properly, then the debiased t-statistic will follow a normal distribution. So this is the debiased estimator. The XD is the XD lasso that we propose in this paper. It subtracts the true value divided by the estimator of the variance, then it will be asymptotically normal, centered at 0 unit variance. Therefore, we can just compare the absolute value of the t-statistic with 1.96 to decide if we want to reject the null hypothesis or we have no evidence of rejection. I would also like to mention that for different underlying regressors, the denominator here will have different rate of shrinking to 0. If it is a persistent regressor, then it's gonna go to 0 at a faster rate than when W1 is stationary, right? So it still preserves some better power if the underlying regressors are persistent, that is to maintain the strength of the signal. Although it shows that the larger is tau, the better is the rate of convergence, but we don't want to choose the tau to be close to 1 because we want to accommodate a bigger S. All right, so this slide is a demonstration of the simulation result. In the simulation, we try two different types of innovations in the regressor. One is RID, another is AR, but in these two cases, the results are actually quite similar. In our parameter, the true parameter, we specify some regressors have non-zero coefficient, but most of them are just 0. Again, for the stationary part, some regressors are non-zero, and most of them are 0. We try different sample combinations of sample sizes and the dimension of the problem, these px and pz. In the simulation, we always choose cz equal to -5 and choose the tau equal to a half. So that is the way that we construct the IVX. These graphs shows the size and the power of the test statistic. So here, of course, lasso requires a tuning parameter, and in practice, we always use in the time series context, we use block tenfold cross validation to determine the tuning parameter. And we test the null hypothesis that the first coefficient is equal to 0. Here, you can see that no matter it's RID innovation or it's AR innovation, we have accurate control of the size of the test. And in each small subgraph, when this is to fix the dimension of the problem, and when we increase the sample size, the power curve is getting higher, right? So this is so we do have consistency. So these results are consistent with our theoretical prediction. I want to highlight the importance of IVX with this slide. So here, in this diagram, the black line is the density of standard normal distribution, and the orange one, the pink curve, is the histogram of 1,000 regression, the histogram of the t-statistic. So you can see that our proposed IVX debiased lasso estimator, the resulting t-statistic works very well, right? It closely follow the asymptotic normality. But if we just do the dispersed lasso as Zhang and Zhang, the original paper, did without IVX, then the result is very bad, right? We can see there is obvious deviation from asymptotic normality, right? Therefore, this graph shows that the IVX step is essential when we are working with persistent time series. This slide shows the power curve with different underlying regressors of interest, right? Because in our main theorem, we show that when WI is W1 is I1, then the denominator converges to zero faster, so it should have higher power. And this theoretical prediction is verified by this slide. We indeed see that if the underlying regress of interest is in I1, then we have higher power curve than the case when the underlying W1 is I0. So finally, let's go to the empirical applications. The first empirical application is in macroeconomic setting. We look at the predictive Phillips curve. It is well known by every undergraduate that the Phillips curve describes the relationship between unemployment rate and inflation. And Phillips curve is named after A.W. Phillips in his famous 1958 paper. But indeed, if you go back to history, it was Irving Fisher who published a paper, 1926 paper on JASA, talking about a statistical relationship between unemployment rate and the price changes, right? And there was a JPE paper, lost and found, to say that, oh, indeed, there is such a paper to confirm this fact. Therefore, we should name the Phillips curve as a Fisher curve. But anyway, in our exercise, we use the Fred MD data. We have 113 US macro variables starting from 1960s. We use monthly data. We constructed the inflation as the log difference of CPI. This is our dependent variable. And the key covariant we're interested in is the unemployment rate. We use all the other macro time series as controls. So we have a regression with more than 100 regressors. The data set provides the T code that is a suggested transformation, right? Because the original time data has all sorts of different types of regressors. But after we follow the T code transformation, if we run a simple AR1, we still find that 10% of the regressors can have AR coefficient larger than 95%. Therefore, it is essential to consider the persistent regressors in our predictive regression. And if you look at the Phillips curve in textbooks, there are a lot of specifications. Some are predictive, some are contemporaneous. Mankiw argues that the predictive Phillips curve has more policy relevance. So because we look at the predictive regression, so we look at this predictive Phillips curve. This graph, the black line shows the Y variable, that is the inflation, and the dashed line is the unemployment rate. you can see the unemployment rate is much more persistent than inflation itself. When we run this predictive regression, we compare it with two competitors. One is the IVX, the low-dimensional IVX with a single X regressor, right? That is the low-dimensional IVX implementation. And the second alternative is the debiased lasso, as in the original paper by Zhang and Zhang, without considering the IVX to accommodate persistent regressors. If we implement the IVX or the D-lasso, we find that in full sample, both of these cases are highly significant. But if we use our XD lasso, we find there is no, in the full sample or in the subperiods, these subperiods are the pre-vocal period, the vocal Greenspan period, and the more recent Bernanke, Yellen, and Powell period. In either the full sample or either of the subperiods, there is no evidence of the existence of a statistically significant relationship in the predictive Phillips curve. Right, so our finding is there's no Phillips curve. The second example, look at the predictability of stock return. So we know that Ivan Fisher's life experience with stock market was a bitter experience, right? He lost all his wealth in the Great Depression, and he has been in debt in the rest of his life. But indeed, the stock is difficult to predict, even if Urban Fisher has a second life and look at the predictability today, right? He will be amazed that with such big data, with such sophisticated models, we still find little evidence of prediction. That is because of the nature of the stock market, right? From this observation, Urban Fisher might find some relief of his unfortunate experience. Again, we're gonna use the Fred MD data, and the Y is the monthly return of the S&P 500. We look at the log earning to price ratio and use all the remaining regressors as control variables. Again, we're gonna compare it with IVX and D-lasso. Our finding is similar as before. Because here, IVX only include a single regressor. And a single regressor, there are like more than 100 other regressors, right? If a single regressor, although they find like a significance with a single regressor, but it might only because like the earning to price ratio is correlated with other regressors. Therefore, they find we find a significant result with the simple regression of IVX. Secondly, with D-lasso, we have shown that the D-lasso is not a proper method. It's substantially biased in our simulation, right? Therefore, we also do not trust this significant result. And if we run our XD lasso, we find no evidence of predictability in the full sample. We find a little bit marginal predictability in the first period from 60 to 93, but there's no evidence of predictability in the more recent decades. All right, so this is the last slide of this talk. In this paper, we provide asymptotically valid inference procedure. We keep an agnostic attitude about the persistence of the regressors. So this is a unified procedure that we don't want to do pretesting. And the key element is an IVX construction so that we can deal with highly persistent regressors. And the auxiliary regression is tailored in our context, which is different from Zhang and Zhang. So it is a combination of IVX and the debias lasso. But since we understand our context well, we are able to tailor the procedure for our purpose. But speaking so much, there is one thorny problem that we have not solved yet. That is, we didn't talk about the practical case when some regressors on the right-hand side are co-integrated. In our published paper, the 2024 paper, we constructed two examples to show that actually if there are co-integrated regressors, but we run lasso, the lasso method is not going to provide you with consistent estimator of these co-integrated variables, right? So this is, even the consistent estimation is not solved yet, not to mention the statistic inference. We are working on this last question, and hopefully we can answer it soon with a fourth paper along this topic to provide a better, even more capable procedure to handle all types of regressors that are under our consideration. So thank you.
Thank you very much, Zhentao, for the wonderful presentation. Let me stop the recording before we move to the Q&A.
Mm-hmm.